Okay, we want to take a look at continuity. Now, we already have an intuitive understanding of what continuity means. Basically, you can think of it as if you can draw the graph on your paper without lifting your pencil, then that thing is continuous. Okay, but in mathematics, we need a little bit more rigorous definition because as you go through your classes, you're going to start getting into weirder and weirder functions, and sometimes that this intuitive understanding of continuity can start to betray you a little bit. So we want to take a look at the different types of discontinuities that can occur. So let's start off with this one. So we have this rational function here at the beginning, right? And then we have a line. Notice if I mute that line, this rational expression just looks like a line. And you go, well, yeah, of course, because those x plus 2's are canceling each other out. But be careful, they're not exactly canceling each other out. They're most of the time canceling each other out, but we can't cancel them when x is equal to -2. Why is that? Well, when x is equal to -2, this denominator is 0, and if we were to divide that out, we would be dividing by 0, because that's what canceling really is dividing, right? So we can't do that. So almost everywhere, those x plus 2's cancel each other out and they're gone, except at the point x equals -2. It doesn't cancel there. So although this looks like a perfectly normal line, and if I actually show y equals x minus 2, they look like they're exactly the same, but that's because most graphing utilities fail at graphing those little tiny holes where a function is undefined. So technically, these two functions are not equal to each other. They're equal to each other almost everywhere, except there's one difference between these two functions. So this line is defined at x equals -2. This function up here is not defined at x equals -2. So although they're very, very close to being the same thing, this one has a hole poked in it. This one does not. So they're technically different. So we would say that the second graph, this blue line, is continuous. This first one is discontinuous, although you're not going to recognize it just by looking at it because you can't see the hole when you look at the graph here. But you'll know by looking up here, oh, there's a hole at x equals -2. Therefore, it's got a discontinuity. It's not continuous right there. Okay. So that's one type of discontinuity that we can run across. Another type of discontinuity we can run across is with y equals 1 over x, right? So notice when x is equal to 0, we get a problem here, right? That problem being that we get a vertical asymptote. And so when you get to a vertical asymptote in a rational expression, undefined, you can't draw this graph and then be able to pick up over here without lifting your pencil off the paper. So that would be another type of discontinuity, right? So generally, whenever you get an undefined point, you're going to have a discontinuity there, because how could you draw across the undefined point, right? You wouldn't really truly be drawing that graph correctly. Okay. We can also get what are called jump discontinuities. So say this was one function right here. Right? See how there's this jump? Like before, we just had a hole poked into a graph. Here we actually have a gap. We have a whole piece missing. So if you were coming up here, you couldn't continue your graph up here. You'd have to lift your pencil up off the paper, put it down here, and then keep drawing. That's called a jump discontinuity. So intuitively, it meets our understanding. Yeah, that looks like it's discontinuous right there. So that's a type of discontinuity. And we can get infinite numbers of discontinuities. There's lots of kind of fun, creative graphs you can come up with that have many, many discontinuities, even an infinite number of discontinuities. And here's one right here. The step function going on forever. It's an infinite number of those jump discontinuities that we're looking at. Okay, so you just want to be able to start to recognize where those discontinuities are, because the way we treat these functions are sometimes going to be different at discontinuities than when we have continuity. All right, couple of things we want to recognize. One, all right, I've mentioned so far a few times, we really like doing calculus on polynomials, right? For a number of reasons. One is that they are smooth, continuous curves. So that's important here. We want to recognize all polynomials all polynomials are continuous unless you do something weird to them. But if you just generally write out a normal polynomial, that thing is continuous over its entire domain. So it is always continuous, makes it really nice to do calculus on. So polynomials are continuous. Rational expressions are close. Rational functions are close, but they don't quite behave quite as nicely. But basically, it boils down to rational functions are continuous except at the points where they are discontinuous, which sounds kind of silly, like, well, isn't that obvious? Right, but all you have to do is go through and find the handful of points for which your rational expression is undefined. It'll be discontinuous there. Everywhere else, you're going to be continuous. So we don't have to worry about any weird continuity going on over here. This whole piece here is continuous, and this whole piece here is continuous. The only place this function is discontinuous is right at x equals 0. So if we're trying to do calculus that involves continuity, some of our tools will say, well, you can do this as long as you're continuous. Well, as long as we're dealing with what's over here, we're fine. As long as we're dealing with what's over here, we're fine. The only place we're going to run into trouble is right here at x equals 0. So as long as we're not worried about x equals 0, we can go ahead and go, well, yeah, this is continuous everywhere else, and we can apply our tools to it that rely on continuity. Sometimes we're going to want to address continuity from an algebraic perspective. So how do we actually put a definition on it? Well, what we basically need to recognize is that a point is continuous if its limit is equal to its function value. Remember, we talked before about a point. A point doesn't even have to be defined in order for it to have a limit. Well, now we're saying a point needs to be defined and have a limit equal to that point if it's going to be continuous. Okay, so when you're just calculating limits, the function value doesn't have to exist there, but if the function value doesn't exist there, of course, we get a discontinuity. So let's take a look at this point 1, 1. So here's our point 1, 1. So what is the function value right here? It's 1. And what is the limit at this point? It's 1. So since our function value matches the limit, then we know this is continuous. So it's kind of nice we have two definitions here. We have the intuitive definition that says, well, yeah, it looks like I could draw that without lifting my pen off the paper, so it's continuous. But that's just kind of a rule of thumb. If you want to actually mathematically rigorously show that it is continuous, then we need to take the function value of 1 and say, yep, that equals the limit, which is 1. So therefore, right here, we are continuous. And you can do that for any points along here, right? We could take this point right here. Well, we can see what the limit value needs to be. We can check that that's what the function value is. If they match, then we're continuous, okay?